Let's see. So the homework was on this paper. About transport, and we did the Clausius clamp run to talk about condensation. And then let's see. Oops, yes, I did the same thing twice. Oops. So a couple people didn't get these things exactly right. Let's see. No, this is the wrong homework. Sorry, that's 3. That's next week's. Let's see. Do I want? So like one person couldn't do this, like couldn't do the derived Clausius, but then like did it for this one, like because the first step in Clausius background is derived the Clausius. So it's kind of odd. Anyway, so I didn't take points off, but it was a little weird. And then it can be used to model the melting point because there isn't that much of a volume change in melting. So you can just get a linear dependence between the melting temperature and the pressure. So that answers that thing. It's almost linear. I mean, it's an almost linear dependence. So, and then this thing is from the notes. I think everyone did that. See, somebody lost points in this, so it's needed for vapor liquid because the vapor is a huge volume change. So that impacts that equation. So you just use the volume of the liquid, volume of the vapor, and then use ideal gas law, and then you get the Clausius quantified. And then the normal plots log of pressure versus 1/T. And it's this kind of the same plot as an Arrhenius plot, and it's kind of the same plot as the Irene plot, and the same plot as a Van Hoff plot. Irene's a little different because the prefactor is 1/T. So it's a little bit of a twist to it, but anyway, they're kind of all the same thing. Basically, log of something versus 1/T, the slope is going to be an energy. And so they all look kind of similar. The difference is that those two, Arrhenius and Irene, are kinetic equations for rates, and the Clausius and Van Hoff are equilibrium. Right, so there's a kind of fundamental difference between them. And then in that case, it's an enthalpy that you get Clausius and Van Hoff, and it's a like an energy, activation energy, or it's some kind of change in state energy for the Irene. So I just thought it was useful to put all 4 of those together because they're kind of the same thing. If a lot of times you're doing temperature dependence of something you're measuring. So it's telling you like, well, what kind of temperature dependence do you expect of things in general, right? Both rate things and equilibrium things. And I think, so your first guess should be log of the thing you're measuring versus 1/T. If that works, then you already have automatically, you have a model, a choice of 3 models that you could use to talk about it. So your model, usually you're doing some measurement, you don't know what's going on, you get some number, and oftentimes you measure it as a function of temperature. You find out it goes up with temperature or it goes down with temperature, right? So then at that point, you say, well, is it going to fit this like log of that thing versus 1/T? Is that a straight line? If it is, then you have 4 choices of the model. Right? So whichever one makes sense to you, and often you could have a kinetic model like with the line mirror absorption model, where you have in fact that's involved here, like you have a monolayer and then it goes to multi-layer absorption on a surface. So that model can be modeled as a kinetic model, where you're modeling the rate of absorption and desorption, the two rate factors, and you can drive the entire line mirror equation, which we'll do later on as a rate law, which would be like basically an Arrhenius approach, or you could model it as an equilibrium model. Where you have like the absorbed and desorbed in equilibrium, which would be like a Clausius-Clapeyron or a Van Hoff, really a Van Hoff. It's like the normal thing for absorption, desorption is a Van Hoff modeling of it. And that both of them can lead you to this line mirror equation. It predicts like gas absorption measurements to figure out particle size and things like that. So anyway, so this is a good situation where you have like 4 choices of making a model. So I asked you to go back and say, so he picked the Clausius-Clapeyron because it kind of made sense to him to model it, and he draws this cartoon. So I asked you to kind of draw a cartoon. I mean, it could have said like do it with an Irene model. So that would have been, instead of saying like there's an equilibrium between the vapor and the absorbed, you could say there's a rate of absorption and a rate of desorption. And those two kinetic rates, the ratio 2 would give you a rate constant, and a log of that would give you the energy, the kind of the energy of absorption or something. It would be like a kinetic model, right? So you could do a kinetic model. You can get the same answer from 2 different ways. And the interesting thing is that, I mean, to me, it's that usually when you talk about thermodynamics, you're talking about only equilibria. Like it's a final case. So like you're doing something, and then finally it will eventually reach this equilibria point. Right? So it's a process of a thing gradually approaching it, and then it gets to it. So that thing that you could someday get maybe would be the thermodynamic answer. And the rate model is going to give you like the actual answer for your like engineering problem, right? The actual kinetics of the thing. But you can solve the same problem and get the same equations, right? And kind of, so the interpretation is a little bit different, but basically a kinetics and thermodynamic equilibria are at opposition to each other usually. Like you say, like with rheology, you can't measure the free energy, for instance, because it's a kinetic measurement. So in any time anybody starts arguing a thermodynamic argument using kinetics, you immediately say that breaks like the first principle that thermodynamics is an equilibria thing, and that kinetics is something separate from that. So it's thermal kinetics, temperature gradients. It's always driven by a gradient, right? So in equilibria, there's no gradient. It's just like the thing that it is. So anyway, so it's kind of interesting. These models can give you the same functionality. So you could talk about this in terms of the chemical reaction model. I mean, I guess the simplest thing would be to just draw a black box around the whole thing and say this thing comes in and it reacts and it ends up being the thing that transports through. So chemical reactions can be, if you don't know the mechanism, they're a black box. Like until you get to the mechanism of the reaction, it's just a box and the thing goes in and something comes out and that's it. Right. So you could use the Van Hoff equation to predict the transport, which is what he's measuring, which is like something comes in, something comes out, as if it was a chemical reaction. And then you could say, like, I have no idea what's going on in the box. And then the Van Hoff equation works because it's a chemical reaction. You just say that, right? So it wouldn't be really giving you more insight than his thing. But his thing, so the details of his thing are not proven by the measurements that he did. Like the idea that there's a 2-step process going on, absorption and then transport, isn't exactly proven with the data that he has. So it could be just a chemical reaction, right? So anyway, I don't think it is, but basically you could argue that it is, and you could also argue that it's a kinetic model. So you could use the Arrhenius, and you could probably use the Irene rate thing if you wanted. So you're going to get the same functionality that he uses to demonstrate his thing. So that's the point. So the idea is like the idea is like you're going to do research, you can get some numbers, then you got to know like what to do with it, and that's where then you're desperate. So you reach for thermodynamics when you're desperate, and then you come up with a model that's based like he did. So he's desperate. He's got this thing. It doesn't make any sense, right? he heats it up, it's supposed to have a better transport. He heats it up, it has a worse transport. So he has to reach into his bag of tricks. His bag of tricks is like thermodynamics. Right. And then he says, like, oh, there's an equation that would have worse transport. It'd be like this Clausius-Clapeyron thing. So bingo, just force fit that and draw a cartoon and you got a paper. And it's, people will cite it because no one else knows what's going on. Right. It's just, it's a kind of a good example of how you're going to, in desperation, reach for thermodynamics to explain things that you're looking at, you know. So, and also, like, you should get used to the idea of developing models, you know, like so using thermodynamics as you can use it as a tool to develop models so you can understand like what's going on. And it may or may not be true. Like you might be rounding off the edges a little bit, you know, trying to fit the square peg in the round hole. But if you can get some kind of understanding out of it, even if it isn't a perfect fit, it's still better than nothing. Like you can predict from that. In other words, he could predict the behavior of other systems by this model, right? So I mean, anyway, it's good to get a feel for that. Like if you're going to be involved in science briefly before you become a corporate executive or whatever, you know, I mean, I think the lifetime of a scientist these days is probably like 5 years or something, right? I mean, some people spend their life doing it, but a lot of people just move on to management or something. So during that 5 years, you should be looking at like drawn models for what you're doing. Like that's the way you learn stuff. That's how you advance the science, right? But anyway, and then explain 2, 3, and 6. That was kind of, he does that in the paper. I think everyone got that. But then the latent heat change with flux. I said that in class, and some people said what I said. Anyway, there's probably some other explanations for this, but the fact that it goes to the liquid latent heat or whatever vapor it is at the end means that at that point he's got vapor liquid equilibria, and then he's got something else here, and the something else is probably vapor carbon equilibrium. And there's a gradual transition as the surface fills up. I think the fit to that line is just, let's see, the dotted lines. It's not that. Let's see. The inset shows the result because of the function of flux. The solid line is a guide to the eye. So he hasn't bothered to use the BET equation. You could use the BET model of absorption to fit that curve. So he could, if he really had a deep enough bag of tricks, he would have reached to like the 2 equations to talk about this phenomenon that he's talking about, which is basically either the Langmuir model or the BET model. And there's some that are higher order models. The BET model, which is a multi-layer absorption model, could fit that curve. Like he could have done that and it would have made the paper a lot more better. You know, he could have explained why that behavior happened. But his bag wasn't deep enough. Right. So anyway, any questions on that? I think like everyone got an A or B on it, but so basically I'm trying to shoot that everyone gets an A or a B, you know, in here. So basically it's good if everyone gets an A or B, but sometimes people aren't getting like perfect, so you end up with like a, anyway. And also I'm only going to give a whole grade. So if you get a 90, it's an A. It doesn't matter if you get 110 or whatever. You can get more than 100 too on the homeworks. If you really smoke an answer, I give you like extra 5, 10 points. Right. So it's possible to get more than 100. So anyway, so basically, the idea is don't get too worried about grades, you know, but try to do this stuff. And it's hopefully it's challenging. So you're struggling to get through it. That's a good situation that I'm kind of shooting for. So anyway, so don't feel frustrated like if things are, I'm not sure if they're too difficult now or what, but basically if they are, it's good. That's what I want you to be, in a place where you're struggling to get through it. Let's see. No editing. And let me see what's going on with these notes now. This seems to end abruptly. No, all right, so I didn't I was fooling through on my phone this morning, but no, that's good. It's got the stuff I didn't see. That's good. So I think we're at 16 or something here. No. I think we finished that, and then I think we're up to here. So if you take that same Clausius-Clapeyron approach, so you say, I mean, when you have a glass transition, there's no change. So between the glass, there's no change in state really to glass transition. Like if you take an X-ray diffraction of a liquid and then of the glass, below the glass transition and above, the X-ray diffraction pattern is exactly the same. The stuff is the same. So it's really like a it's basically a topological transition. Like in terms of a glass transition, the things are just kind of get stuck. It's like when you buy the ground coffee in a bag, in a vacuum packed bag, and it's like a brick. And then if you open it up, so you clip it and you look at the volume changes, like maybe 1 or 2% of the bag, and then all of a sudden it's squishy. So that's liquid, and the other one's solid. The other one's a glass. That's kind of what's going on. Like you have a volume change. So you can think about the glass transition just in terms of the volumes. This is like 1 over the density of specific volume. And then the thermal expansion of the coffee grains when they're with no vacuum is a steep transition. And then once you pull the vacuum out, it's more difficult for it to thermally like compress the volume because the things are stuck in there. The little coffee grinds are all stuck together. So it becomes a solid object like a brick, right? So at that point, the thermal expansion is lower, right? So you can think like even when it's in a glass, when it's under vacuum, there's still pores between the coffee, whatever grind things, particles, right? So that means you have like the occupied volume, and then you have this kind of free volume we call. It's like the volume that doesn't have stuff in it. Right, so molecules have that same behavior. Like there's going to be some kind of void within the molecules. So, and then there's like the actual like electrons and protons and neutrons filling up space, right? Solid part. So there's 2 components, like a free volume and this occupied volume. So it's an idea, right? It's like an idea that isn't necessarily proven, right? So to prove that idea, you go So when you have like E equals MC squared, so if you work it backwards and put in E to get M, right? So square root of E is going to give you M. And then when you do that, so you're going to make matter. So it seems like something you can't do, but you can do it if you have a big enough machine. If you have a synchrotron or you have some kind of particle accelerator, then you can make matter. But when you make matter, there's like certain rules that have to be followed. So you have to have conservation of charge, and you have to have conservation of net matter, conservation of angular momentum, blah, 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 blah. So net charge means that you have to, if you make an electron, then you have to make something equivalent to an electron at the same time. You have to have E minus is a normal electron, E plus is called a positron. But so this is matter and antimatter. So you can do this, people do this routinely. Believe it or not, people make antimatter all the time. I mean, why there isn't equivalent antimatter for the matter that we have around, I don't know the answer to that. But basically, when you create matter from energy using E equals MC squared, you always create pairs of matter and antimatter. Anyway, so these positrons are like electrons, except they're positively charged. In other words, they have the same mass, right? So anyway, anyway, you can make positrons. This place in Germany makes positrons by shooting a neutron beam at a piece of cadmium. That makes energy when the energy decays. So neutron beams come from a nuclear reactor, and then basically you hit a piece of cadmium and it gives off energy. It's the right energy to make an electron and a positron. If you put that stuff into a field afterwards, like the plus and minus, the plus attracts the electrons and a minus attracts the positrons. So you can get a positron beam, use an electric field. And then because of Maxwell's laws, if you put magnets on it, you can accelerate because you have a field, when a magnetic field changes, you get an electric field type thing, right? So if you shoot the positrons down a tube, and then you put magnets, you can make them turn corners. you can basically take those positrons and put them into a vacuum filled tube and have them go around in a circle. That's a synchrotron. You can do it with electrons or with positrons, right? Positrons are nice because when electrons decay, they're going to give off all kinds of radiation, right? But when positrons decay, they just combine with an electron and disappear. Like there's no positrons to combine with electrons. You can't just have them disappear. Positrons will just combine with electrons in the concrete around the building and just disappear, right? So there's an advantage to using positrons, and if you want to make a particle accelerator setup, because it's safer, like you're not going to have electron beams like TEM beams flying at you all the time, causing all kinds of problems. Because once the thing escapes, it immediately combines with any electron, which is a bunch of them, and disappears. It goes backwards of this equation, makes some kind of weird thing, a gamma, which is like a muon or boson or something or other. So anyway, so it's possible to make positrons and they annihilate. So if you shoot positrons into a material, well, the positrons, depending on how much free volume is in the material, the positrons, so if there's a lot of free volume, the positrons will last a long time. I mean, microseconds, milliseconds, right? And if there's no free volume, they annihilate immediately because they automatically hit the stuff that's in there. By shooting positrons at a material and watching the decay beam that it gives off these other particles you can detect, then you can map out like how much free volume is in the material. So this is how people figured out. There's other ways to make positrons, like some radioactive materials just make positrons, right? So anyway, so basically this idea of free volume in a glass transition is more than just like an idea at that point. Like you can measure it. You can measure this free volume, right? And you can measure how it changes with temperature. You can measure how it changes between a glass and a glass and a liquid, right? So you can get the information that's on this kind of back of the envelope sketch. You can actually measure these things, right, with this positron annihilation thing. Anyway, so the idea is like this. They figured out for polymers, when you make a glass, like a water bottle, one of those clear water bottles is a glassy state, and you can melt it into a melt. So it goes through a glass transition. The change in the amount of free volume in the glass is 11.3%. They figured out that number from positron annihilation. And as you cool down the liquid, so cooling down the liquid means that the molecules, so the density is dropping. So basically the density drops, you cool it down, then you reach a point where you reach 11.3% free volume, and then the particles stick together and makes a glass. They can't move anymore. Right? So anyway, you have more free volume in the liquid state, then you reach a glass transition, reach 11.3, and that's where it locks up. So this would be indicated like the coffee grinds and the vacuum pack thing had 11.3% empty space in it. Vacuum, right? That's not occupied by coffee. I'm not sure if that's true, but that would be interesting to look at. But anyway, that's like the free volume concept of a second order transition, glass transition. Right? There's a lot of other second order transitions. So if you do the same analysis for the glass transition, you say that at that point the volume of the glass and the volume of the liquid are the same at the transition, and the enthalpy is the same, and the entropy is the same, and the free energy is the same across that transition. There's no step change in the state functions, but there is a change in the derivative functions. So what he called the thermodynamic response functions, right? In analogy with linear response theory. So the kind of the slopes of the state functions against some parameter is going to give you, there's a transition in those. So there's a step change in the thermal expansion coefficient and in the heat capacity, right? So there's no heat of transition, there's no peak in the heat capacity, but it's a change in the value, right? So anyway, so there's no change in the volume. That means if you say the volume could be a property of temperature and pressure, so dV dt constant P dt, dV dP constant T P, and this is the thermal expansion coefficient. That's the compressibility, isothermal compressibility. So those are numbers from the table. Then V you can measure, and T and P you can measure. So you can, if you say that delta V is 0, you find out that there's the pressure dependence. So the temperature glass transition is proportional to the pressure, right? Which is kind of verified in this paper by Casalini and Ransom. So these guys are at the Naval Research Lab, which is in across the river from Washington, D.C., Anacostia. It's like, so D.C., like the DCA airport, used to be National Airport. And across the river from that is Anacostia. There's also like the sewage treatment plant for DC is there. So it's kind of an area that smells. And also Anacostia is kind of like a bad slum. Like if your car breaks down, you just keep driving as if you can there type thing. So anyway, at the tip of the point that reaches out into the Potomac River is this national lab, this Naval Research Lab. And the Navy has a ton of money for research, like because they're doing kind of sophisticated things, I guess, to make ships, whatever, aircraft carriers and things. So it's a big money lab. They give money out for grants, and they also have their own research thing. It turns out like that lab became somehow the center for glass transition studies for some reason. Like a couple people there were experts in that, and they hired more people that were experts in that. So they built up kind of the Navy has like all the stuff on glass transition. They get the best people and the most money. And if you're doing research in glass transition, you get money from the Navy. It doesn't make any sense really, because they're usually dealing with a liquid, not a glass, like water, you know. So I mean, somehow that's the way things work out. I mean, this paper's, it's like 2020, it's by these two guys, and it's kind of it shows you a little bit about, it's on the webpage, you know. So anyway, so the thing about all these second order transitions is that they're rate dependent. So you have to think about like you're cooling down. So you're cooling down and trying to get to this glass transition. Well, if you cool down fast, like you can zip right through that and then lock it in a little bit later. And if you cool down slowly, it moves up to a higher temperature. So it's not a fixed target. It's not like a melting point is pretty much a fixed target. It melts at a certain temperature, right? But the glass transition moves around depending on the rate, because you're talking about the motion of the molecules, which is a rate, right? So you kind of, and your cooling rate is also a rate. So the rates have to match up. And if they don't, you shift this temperature around. And you can get things like if you cool it really fast, you can lock in a residual kind of stress in the material that will release when you heat it up. So you get like an enthalpy of transition. It's an apparent enthalpy of transition for the glass transition, right? So it's kind of an odd transition to look at, but in that sense, it's interesting, you know. So they talk about, so you have to talk about at a certain rate that you're doing this cooling down, right? So these guys have like Tx, X is like the rate that they cooled it at. So these are isobaric, isochoric, so it means the volume's constant. So it'd be like if you put a material into an autoclave, so a fixed volume system, and it's also got a fixed density because the amount of material in the system. So you have an autoclave that's closed, it's got a fixed amount of material, means that the volume's fixed, but the mass in it is also fixed, so the density is fixed. And so you have isochoric, means you have a fixed kind of density system, which would mean like you have an enclosed system, right? You got to change the temperature, the pressure increases when you change the temperature, right? But basically, this is the glass transition temperature measured in a system of varying pressure. You pressurize it, and then you get a different glass transition, and they're linear. The plots are linear following this thing, dP, dTg is a constant, and the slope of that's going to be, if you do T versus P, it's going to be the compressibility by the thermal expansion coefficient. So those numbers could be looked up. This paper was kind of useful to look at, but it's like confusing too. So this is under here, and it's like let's see. So this is the right part. Single component systems, gelation, icing, TG for single particle. Glass transition is a function of pressure. Here, that's that paper. So I mean, it's kind of worth looking at this. He's got just, all right, it's really confusing, but he ends up with these things called scaling coefficients. So these gamma things. So he's got, and then right. So people really get into glass transition. That's the point of this. Like they get in so deep into it that you don't know what they're talking about. It's like gets to be crazy, right? So his X parameter is the time. So he always has like the relaxation as a function of X, like what's the rate of cooling the thing, right? And then temperature and density is raised to this gamma thing, which is this scaling coefficient. It's like the density definition of the scaling exponent. And then he kind of defines it. So anyway, so with these scaling exponents, they talk about hard and soft transitions for the glass transition, or brittle and not brittle transitions. So, and that gets into a whole, so there's like literally thousands of papers written on these scaling exponents for glass transition, right? And for various kinds of second order transitions. There's like maybe 10,000 PhDs on this subject, you know, like around the world. And in places like France, like they're really into this. And then Naval Research Lab is one of the top places. Anyway, most people couldn't care less about this. Basically, it is a subject. It's got to do with thermodynamics, and it's basically there, you know. So probably you should kind of know that there are scaling coefficients. They have something to do with glass transition. There's different kinds of glass transitions, etc. Right? So, but and then bottom line is he's showing that plot that thing's linear, and then from that slope, he gets this exponent, and he gets another exponent that's supposed to be the same thing, but it's different, and he kind of talks about that in here. So again, like these are also linear. He gets another exponent from this. He compares the two exponents. That's the gist of this paper. It's a little bit too involved to give as a homework, because the only thing that we would get out of it is like this plot verifies that it's linear, which you can calculate from thermodynamics easily, like straightforward, right? But the rest of it is pretty involved. I mean, we don't really want to look at it, I don't think, because it's going down a wormhole, you know, that's too far down and there's not enough benefit from going down that hole. So, but anyway, it exists. I think I just want you to know that kind of thing exists. And the free volume, the positron thing. Then if you, all right, so polymers, glass transition is important to polymers because you have like a glassy state and a semi-crystalline state and an amorphous state polymers. So you have like the polymer, like polyethylene, and then it's a goo, you know, when it's a melt, it's kind of like really thick molasses and really hot. Then you cool it down and it's going to crystallize. So in the glass transition of polyethylenes isn't really measured, but it's something like 40 K. So it's like minus 250, 30 C or something, right? So it's like you can't measure it. It's not, you don't have a normal lab machine to measure the glass transition of polyethylene. So it's semi-crystalline, and low density has like maybe 40% crystallinity, and high density has like 80% crystallinity. So anyway, so it's a semi-crystalline. So it's like this jug is high density. So it's a crystalline, semi-crystalline material. That's why it's like flexible. Like if it was a solid crystal, it would be like a rock. Flexible because it's got amorphous zinc crystal in it. Right? But and the TG is so low that it's just a liquid with kind of bricks in it, crystalline bricks, right? So anyway, but other polymers like PET, so like water bottle, like this thing. So this, like the cap is polyethylene like that, and then the bottle is this PET, right? If you look down at the end, it's white because it can crystallize. So when it cooled slowly, it crystallized. But when you cool it fast, so the thin part just cools fast and makes it glass, right? So it's a glass. It means it's like got the same structure as a liquid, but it's stuck like the coffee grinds in the bag, right? So anyway, so there's some kind of laws for polymers because of chains, and they're based on the free volume idea. And one is this Corey-Fox equation, which says that the end groups, so polymers are just chain molecules, and the end groups have more free volume because they shake. It's like a dog's tail wagging. So it's got more free volume at the ends. And then these have less free volume because it's the rest of the tail and the dog. So the dog doesn't move much, but the tail moves a lot. Basically, it shakes out free volume. So you can say like the number of end groups in it So if you take the molecular weight, so if it's 10, then 1/10 would give you kind of the percentage n groups, or 2/10 would be like 2 n groups per 10. If it's 100,000, it's 2 n groups per 100,000. So some number over the molecular weight gives you like the percent n groups in the material, which would be like that should lower the glass transition because it's got more free volume. Right? So if you follow that mapping, if you increase the free volume, it becomes a liquid. So it's kind of the idea. All right, so you take the glass transition of an infinite molecular weight chain with no n groups, and you subtract 1/mn, and you get the glass transition of polymers at different molecular weights. Right, which would be important if you're making bottles like this. You want to know what temperature it's going to turn into a glass, because you need to quench below that to get it to lock in. Right. So anyway, so there's these kind of rules, and so this works perfectly, like absolute 100%. Right. So there's other rules based on that. I talk about when you mix two polymers with different amounts that have different glass transitions. That's called the Fox equation. But so anyway, this one though is based directly on the free volume theory, and it's verified by that. For water bottles, but right, so I think that's all I have. There's a lot on glass transition, but it's not usually covered much. I don't know why, but basically it isn't covered much. I think partly because it's not that well understood compared to first order transitions. Because it's kind of it's a funny transition in that it's a moving target. If you cool it faster, you get a higher temperature. It's not kind of a comfortable place for thermodynamics. You don't get a fixed number, So, but there are people like naval research that spend all their time just looking at glasses, and there's other kinds of first and other kinds of second order transitions. In particular, the first second order transition that was studied, it's like first second, is this Curie transition. And all right, this is also debatable if it's first order or second order. Like sometimes it's first order, sometimes it's second order. And there's also this Néel temperature, which is like the Curie temperature made more complicated. But they're kind of the same thing. They both involve arrows. So you have a ferromagnet is a magnet, like your normal kind of magnet. So it's got a north-south pole on it. And then if you heat it up, those poles thermally kind of spin around, right? And then you get to this place where you don't have a magnetic moment and it's not a magnet anymore. You heated it too much, it's not a magnet, right? But that material, which is like steel, right? If you put a magnetic field on it, you can magnetize it. So steel sticks to a magnet because it's a paramagnet. When you put a field on it, it aligns, right? And then it sticks to the refrigerator, like a refrigerator magnet thing. Or the refrigerator is a paramagnet, the refrigerator magnet's a ferromagnet, right? So anyway, thermally, you can go through a transition between these two. And this is where the order parameter concept came from. So you'll see people talking about order parameter and they're talking about density. Or they'll talk about order parameter in a binary mixture and it's the composition. Right, so when you get to a phase separation point, you get the average composition minus the density, average composition minus the composition at a point suddenly gets a value because it's not the average composition. You've separated into two kinds of materials. Right, so that's a transition in the order parameter, which is the composition. Same with the density, like if you have the average density and you crystallize, suddenly there's a change in the density. So that's a change in this order parameter, which would be the density. In this case, it's the arrows. So you talk about the magnetization, like the bulk magnetization. When you go through this transition, there's a change in the bulk magnetization. It goes from 0 here to like some value here. Right, so there's a change and literally this is a change where it orders. So that's why they call it an order parameter. But once you get to density and composition, which are the normal places where people operate, then it doesn't have anything to do with order. It's just got to do with that they borrowing the terms from this magnetic thing. So that kind of makes you, and then so the Néel temperature is when you have this anti-ferromagnetic, or Néel is when you have a ferrimagnetic, which is partly oriented. So you have like if it was a magnetic field, it was just charges. You have like NaCl. So Na would be plus, Cl is minus. So maybe you'd have like a salt would have a thing like this, right? We have some would go one direction, some go to the other. And in that case, if you go from that, so it might not have a magnetic, might have magnetic domains that are oriented to ordered. They might go to disorder, but might not have a magnetic moment overall. Right. So anyway, so this is kind of like things that maybe don't matter that much to us. Right. But so this is normal magnets over here, ferromagnetic, paramagnetic. Anyway, so this idea, so I guess around 1920s or something, this was like a topic everyone was interested in because no one really understood what was going on. So the icing model came out of this, and then the Metropolis method for computer simulations came out of this arrow thing. And then this guy Landau, right, is kind of used this is his main theme for talking about how transitions happen, right? So first and second order transitions, how you could model it. He was basing it on this magnetic transition things. So anyway, so basically he wrote the book on it. Like he invented first order, second order concepts based on this idea of magnetic things. And he also invented the order parameter to talk about these things. Right? So in that sense, so maybe there's not that many people working on magnetic moments now, but basically the whole theory about transitions comes out of his stuff. Right? All the terms that you use are from his stuff. So if you don't kind of look at briefly at his things, then you won't know why you're looking at an order parameter when you're talking about density or composition. Right. So it's like they borrowed from that to get the this business. So he said he said he had this system and it's obvious to him and maybe you too that there's order to one and there's not order to the other. So there has to be an order parameter that would account for that. In this case, the order parameter is a magnetic moment that's generated by these moments lining up in the material. Right. So somehow you should be able to write an expression like the free energy is a function of the order. Right. So the free energy, depending on the temperature, it will go, and when you get above the Curie temperature, it goes to this state. When you get below it, you get to that state. So you have a high order parameter here, low order parameter there. In both cases, you should be able to have an expression that talks about the free energy as a function of that order parameter, which is gamma, capital gamma. Small gamma is the kind of thing, it's a squiggle. Capital gamma is that thing. So, all right, so anyway, he said that this thing had to be like, so he says it's going to be a Taylor series. I mean, this is like the first thing that you do. You say like, it's going to be just a polynomial. This is what Excel does, right? Like you go to fit a curve in Excel, it gives you a polynomial. It's like the idiot's guide to fitting curves, right? So you could fit even the log whatever versus 1 over t as a polynomial if you wanted to, but it would be just like you get no understanding out of it. Like you wouldn't be able to get the energy out of that, right? So, all right, so he just says like it's going to be a polynomial. Then he starts to say some things about like what kind of polynomial it's going to be. So he says it's got to be like even powers of this thing, and then it's an analytic function of gamma and temperature. Free energies has to be symmetric in gamma, so it has to be, because it's got to be symmetric, it can only be even powers of gamma. So he has only like gamma squared, gamma 4, and then he has these thermal kind of constants as prefactors to it. So he's using the Helmholtz free energy instead of Gibbs free energy because basically he's talking about a box of fixed volume here. Right? It's not an experimental system or at atmospheric pressure. It's a box of fixed volume. It's like it's natural when you're talking about theory to talk about Helmholtz free energy, which is going to be related to the Gibbs by PV at PV, and then you get the Gibbs free energy, which is the thing that we want. So your models are always going to be Helmholtz free energy. What you actually want is Gibbs free energy, but there's a way to do a transition between them. You know, so anyway, so anyway, he says it's going to be this even orders of this thing, and so this is the kind of behavior he gets out of it, and that's what you want. When you're above the Curie temperature or the critical temperature, so you can call it the Curie temperature for magnets, but if you want to generalize it, it's the critical temperature. It's where things happen, right? So when you're above that, then if you look at the free energy, so you want to minimize the free energy, right? So you minimize it on that curve at 0 order. So gamma is 0, that's the lowest point of free energy you get. right? And then when you cool it below the Curie temperature, it makes a ferromagnet. Then you're going to have a certain degree of order in the system. And this gamma thing has to describe that. So it has to be that, well, if I have this much order, it wants to relax to that much order. If I have this much order, it wants to relax to that much order. So I reach a happy point where I'm going to get the order of the system. Like it's not going to be perfectly ordered the same all the time. It's going to be like some transition between like this state and that, this state and that state, like going between those two. Right, so that's the general idea of what he wants. And he can get that with this simple function. If he says that this A term changes sign when it gets to the critical temperature. So if I'm above the critical temperature, A is positive. If I'm below the critical temperature, A is negative. And when A is negative, then I have a square term and a quadratic and a fourth power term, right? So basically this isn't changing as fast as that thing. So initially this thing dominates, so it drops, it's negative. And then after the positive thing takes over and it shoots up like a banshee. Right, so it's kind of like balancing between a negative term and a positive term gives you a minimum of the thing. It's kind of a simple, it's kind of simple, right? So, but with this, he can start, so if he says that that's the free energy, again, he invented that, then he can say like, well, at the transition, at the critical point, all the derivatives, so the definition of a critical point is that all, so everything goes flat there. In other words, I showed you before, we plot the, like the Gibbs free energy versus composition, I mean, you're at the critical temperature, it looks like that. If you're below the critical temperature, it's going to look like that. So it's got two minima, and the slope of that is chemical potential. And the two chemical potentials are equal. Right? When you get to the critical point, it goes nuts. So at these points, your dg d phi equals 0. At that point, d squared g d phi squared equals 0, just by the shape of the curve. It's inflection, right? And then d squared, this is d cubed, and d squared is the inflection point. D squared g d phi equals 0. So at this critical point, all those are true, like dg d phi equals d squared g d phi squared equals d cubed g d whatever equals 0. They're all, because it's flat. So for a flat line, every derivative of it is 0. So it's flat line. And so it's basically, this is a common tool used to analyze state functions when you get to the critical point. So you have like, this is the binodal point defined by the first derivative 0. That's called the spinodal point by the second derivative. And this is a critical point by the third derivative. Well, we are actually at the critical point, all three of them match up. So that's what he's doing. And that, I'm not sure if he invented that or what, but basically he kind of invented it, you know. I mean, more or less kind of invented that. So because this free energy expression is going to be of that type, right? So anyway, so basically he's got like the first derivative has to be 0, then he gets an equation. That means he can, so he's trying to solve for two parameters and needs two equations. And then the second derivative is 0, there's another equation, and they can solve for this is the order parameter at the critical point. So because say the first derivative and the second derivative both equal 0 and equate the two, you can solve for the two parameters A naught and B naught. And then he can solve the whole thing, and he finds out that the critical point of the thing is going to be T minus TC to the 1/2 power. So he calls this the critical exponent, this 1/2. So meaning you could have other critical exponents. Right. So he's kind of leaving the door open to like he could fiddle around with this. Like he could measure this critical point as a function of temperature, and then he could see how it changes with what power it goes to, and then he could have a critical exponent. It could be bigger than or smaller than 1/2. And if it's larger or smaller than 1/2, it's different kind of critical phenomenon. You see, so we can set up a whole framework and get more and more research money to do research on starting with a simple idea and then saying like it's going to branch into this. We need to know about critical exponents now. That's going to be another 10 PhDs. Right. So it's kind of the idea, like you start something and say like, oh yeah, it could go there and then there and there. It's a rabbit hole thing, right? So anyway, the basic idea is just the valid part that this is how the thing should behave. right? So anyway, so that's good, you know. So then he can, then once he has the free energy, he can talk about calculating the parameters like the enthalpy and then the heat capacity in particular. So you know that the heat capacity is going to kind of define the kind of transition that you have. So if you have a heat capacity that has a discrete transition, then basically it's that's a second order transition. Like you're going to have a different value of heat capacity above and below. And then, so you can define that this is basically ends up being a second order transition by calculating the heat capacity. It says this is the expression for heat capacity, dHdt. I did this kind of a couple days ago, classes ago, right? But dHdt P, and then dsdt constant P. So he does the derivatives of F to get these things. First derivative and the second derivative just gives you Cp by T. And then he can write the second derivative because he solved for the A0 and B0 by talking about the critical point. And then basically you can get an expression for the heat capacity, right, for this thing. And basically the heat capacity is going to, above the critical point is 0, and then below the critical point, it's going to follow this equation. So it's going to be linear in temperature, and it's going to be this A naught by B naught. A naught squared by B naught is just going to be this dependence of the heat capacity. So the discontinuity in heat capacity is like a change in the thermal expansion coefficient, right? That means it's a second order transition. So if it was a first order, this guy would have a peak in it. So you'd have an enthalpy of transition would be the integral. So again, like heat capacity, when you measure in the DSC, you have the two pans, you're heating them to keep the same temperature between the two pans. So you have to put more heat into the thing that has stuff in it because it has heat capacity. So heat capacity is a measure of dq dt. So it's a measure of the enthalpy that you're putting into melting, right? So if you have a transition, when you get to the melting point, you have to put a lot of heat in just to keep it at the same temperature because it takes heat to melt the crystal. It's the first order transition. Cp will have a peak in it. And if the second order transition, it's just continuous through that and it changes slope, right? So you just have a change in the value. You don't have a peak. So there's no enthalpy of transition. There's no peak. So anyway, his first approach to it was nice, but basically they kind of wanted a first order transition out of this, and it's a second order. Right? This looks like a first order transition. It looks like you have a crystal and it melts. That should be a first order transition by anybody's random guess, right? Basically, when he does this little model, he gets second order transition. So anyway, it's possible to get that to be a first order transition by several methods. So you can imagine, again, this is like the first PhD did that one. The next PhD is going to do like, how do you get a second order transition? And there's 8 PhDs doing it. So they get 8 different ways to do it. But one of the ways you can get it is if you have, if you write the expression like this, you have, and they're capital because there are different parameters, right? Instead of small a, small b, it's big A, big B, capital B, capital A. But you put in a third order term in order to get this kind of the first order transition that you want. So basically, let's see. So when you get to the transition, the A term becomes positive. So it's negative below the transition, positive above the transition. And then you have this, because you have this, so you have T naught with A, but basically there's going to be a T star introduced into this, which is so you have regions T to T star, and then T greater than T star, T less than T star, and then T greater than T naught, but less than T star. And the behavior is going to be different for the different regimes of that. And then you can solve for this T star by doing kind of the derivatives of this thing. Right, and you end up with an expression that says, what is this T star for this condition? And then, so basically through this business, he invented the idea of like first and second order transition. I mean, you can weasel through this and the math of this thing, but basically the point of it isn't necessarily that this is going to predict how things are, but basically that this is where the terms like first and second order came from, the term order parameter, right? So all these things, and then all this math is kind of ported into by changing the order parameter from actually the magnetization into density. And you can talk about a single component system. And by changing it to composition, you can talk about like a binary system where you mix two things together and they phase separate. Right. So basically, this becomes the basis for a lot of, so you'll see the terms coming up in papers. And then, so that's the point of it, is just like if you see those terms and you can kind of go back and say, like, what's going on with this stuff. That's all I'm going to say about Landau today, unless we run into it in a paper or something. But so we can revisit this later on. But basically, it's just to introduce these ideas, you know. Let's see what else. So yeah, so the traditional thermo, like you probably heard of this. The compressibility factor, the Z thing. So if you have ideal gas, it's like PV. So rho is 1/V. So PV equals RT if it's molar, plus molar volume. So it's really V/N. Right? So, or N/V or whatever. So for density. So that's the ideal gas law, P/RT rho. And then if you say that this thing would be 1 for an ideal gas, like PV/RT would give you 1, right? So then you can say, well, there's going to be, for non-ideal, there's going to be other terms involved in this. So ideal gas means that you have, like initially there's, I don't know if this guy works. No? So you have some gas atom, and it can just pass right through another gas atom. Right? So it's like 1, 2, no problem. So there's no excluded volume. No excluded volume. That's kind of number 1. 2, there's no interaction. There's no like this guy plus that guy like each other. Like there's no attraction. So those 2 features are features of ideal gas that are a problem. Like it's nice, you get a nice simple thing, like you plot P versus V, and it's going to be this kind of curve. So this is a specific volume. And so it's going to be that 1/V curve. That's when you see that, when you heat up the gas, even water, steam at high temperature behaves that way perfectly, like just like an ideal gas. And so that can be like verified, but when you cool it down, like different stuff happens, you know. So when you cool it down, this is what happens. So this is steam. So it's that nice curve. This is an ideal gas. So it's kind of with the P versus V. And as you cool it down, suddenly this thing kicks in, right? So you have something else going on. Something else being like, simplest case, excluded volume. And next, more serious case, attractions. Because if you want to form like, so this is a 2-phase region here, and this is these are isotherms, right? So when you want to form a liquid phase at high density or low specific volume, and you want to form a vapor at low density or high specific volume, then you got to have like something go on. Like you have to have the things have this kind of attraction that go on. Like you need to have that attraction in order to make a liquid state. The things have to want to form a solid. You want to have to collect together. Right? So anyway, you can start with the so the van der Waals is like the simplest. Let's call it cubic equation state. So or EOS. A lot of times you see EOS in equation states. You have P, which would be like RT/V, right? That would be the ideal gas law. This is specific volume, has an N in it, right? You say minus some excluded volume. So it's this excluded volume is feedback. And then you're going to have like you're gonna have an attractive, so this thing, so the B serves to increase the pressure. So the pressure increases because you're dividing by a small number, so that boosts that. That makes sense because if you have things they have to bounce off, that means there's kind of effectively more things. Right, so that means the pressure has to increase. Whereas this thing should decrease the pressure because you're pulling things together and it's condensing, it's gonna have lower pressure, right? So you have to have minus A, and that's gonna have like the density squared. So this is V squared because it's binary. Binary means you have to have two to tangle, right? So it's always gonna be like two. You can make it that it was 3, and then you have some other term over like V cubed. And you have another term over V4, V ternary, ordinary, continue it on. But at a minimum, you need binary to make a liquid, right? At a minimum. So the simplest case would be like that. That would be an equation state. That's the van der Waals. You see? If you work this out, you end up with a V cubed term, and it ends up being a cubic term, cubic expression. Like you write it out linearly, in the form. Anyway, so that in fact, like the van der Waals can predict the whole phase diagram here with 2 parameters with this excluded volume with an attractive interaction. Right, so you can predict almost like everything with that absolutely simple model. Right, so that's kind of where we get to in this thing. Let's see. So where am I here? It's all Landau stuff. So before you got to van der Waals, so there's this idea that you could, so you saw that Landau's using this cubic, this kind of Taylor series expansion to talk about free energy, right? But he didn't invent the idea of that. That was invented, this guy, OH something. I forget his name, but it's OH something that invented this idea of viral. Maybe I wrote it down here, not him. So anyway, it's basically, all right, so you have A, which would be the ideal. It's a constant, this compressibility. And you're going to add in like terms and density because you're going to have like, the first one would be binary, even though, because there's a row already here. So B rho is actually rho squared. Like I could do Z rho and it'd be A rho, B rho squared, C rho cubed. This is binary interactions, like basically like the van der Waals A term thing. This is A. Attraction, this is an attractive interaction, excluded volumes. So, okay, so B, the second Viral coefficient is a lot like the van der Waals excluded volume, except it's a little simpler equation, so it isn't exactly. So basically, you can say what B is. It's going to involve B ends up being B. So B, this B. If you make these two equal to each other, you get that B is B, and then it's like minus A over T, like that. And so this is called the second Viral coefficient. So anyway, this thing can be measured with light scatter. So if you take a solution and shoot a light beam through it, from the intensity that you get in the scatter, you can measure the second Viral coefficient. If you want to adopt the van der Waals model, you can get the excluded volume, the subtractive interaction from the B. If you do a temperature dependence of that, right? So anyway, so this is like, in other words, another way to look at it. There's like a hardcore repulsion part to the excluded volume, and so that, in other words, B is accounting for all the binary interactions, both repulsive and attractive. In other words, van der Waals excluded volume is a repulsive interaction, and this is an attractive interaction. You can have both. So if you want to make a liquid, you have to have this. If you want to make it look real, you have to have that. Right. So basically, you kind of have to have both. And this Viral coefficient takes into account both this excluded volume and the attraction, and they balance against each other. This is attractive, that's repulsive, so there's a sign difference. Right. And then this kind of thing, if you bring up the temperature, right, then this thing has less effect because these things are also subject to like KT motion all the time. So this attractive thing is going to diminish as you increase the temperature because the temperature is making it shake and bake. This is making it kind of sit in one place. So they're opposing, you have a ratio of those two. And then this guy is not affected by temperature, like it's still going to exclude matter if it's really hot or cold. it's still gonna have a brick there that it can't get through. And so it kind of makes sense that you can solve that and get this, but basically you would write that out anyway. Like you'd probably write it that way if you just guessed it, how it would relate. And C is a ternary, is like three things interacting. That's like a morphological interpretation of this, right? Another interpretation, so there's many interpretations of what these things are. Another interpretation is that A is if you have spherical molecules, the particles, and B is like if you have a kind of cylindrical, so it's got two directions to it. And then B, so it'd be like B, A, and C would be like if it's somehow, I don't know, some other shape factor, like platelets or something. The people have interpreted A, B, C in terms of shape. They've interpreted A, B, and C in terms of the van der Waals coefficients. And I think there's like three other ways they've interpreted those things. So you'll see like, so this would be like if you're doing like biologist and you're looking at cells, like tobacco mosaic virus would have a B because it's a rod. And if it's some other kind of virus, it's got a C because it's got a kind of a curvature shape to it or something. Right. So biologists like that kind of picture of it because the thing they're looking at is the shape of these bugs or something floating around, right? Or whatever. And then chemical engineers like this because it's like kind of like oil mixing type thing. And then other people like different things. So you can kind of force fit this kind of binary ternary or shape and some other things into those if you want, So again, it's like it's a model that's popular. If you propose a viral expansion for measuring thermodynamic behavior or something, no one's going to argue with you because it's like been in all the books. And if you interpret those parameters however you want, it's pretty much a Wild West. You can interpret them however you want, but the simplest way is just the single thing, then the binary interaction and whatever. You would never use C or higher. Like nobody ever uses anything beyond B. This base, except for biologists who use C for this. And actually, sometimes people use C out of desperation. Like if you reach the wall or it doesn't work anymore, you include C and say like it's ternary things. For instance, like if you look at like polymer chains, and you look at they expand thermally, right? So that expansion you can fit with A and B. But if you want to go the other way and say it's like proteins or DNA, and then it collapses into like a folded protein, then you need C. I mean, and theoretically they use C there to describe that transition, called the coil collapse transition. Right, this is coil expansion. So basically, and this is called the theta condition of the critical condition. Right? So basically, people will reach for C when they have no way to describe what's going on. Like, how does DNA fold? Well, you need to use C to do that. Or they think they have used C to do that. I'm not sure you need to use it, but they do. Right. So anyway, so this is that business. So this is just showing, and I think I showed last time the supercritical fluid thing. So this is again, this is like putting material into an autoclave. So it's a fixed volume, fixed amount of material. And then you crank up the temperature and the pressure changes. So you start with a certain amount of material, and that's going to decide at a certain temperature, and that's going to decide kind of your starting point on this. So you can put more material in, you get a higher pressure, put in less material, you get a lower pressure. And then as you raise the temperature, it's going to go from a solid state to a liquid state, and then keep raising, you're going to get to the gas state, right? If you put in less material, it can't make the liquid state, so it just goes from solid to gas, right? So it'll just sublimate, they call it. And you sublimate from the solid to the gas. And if you put in too much material, you get to this critical point where there's no distinction between the liquid and the vapor. And I showed that. I showed a video of that like a while back. Well, we got everybody here today. 6 people. That's pretty good. Nice. All right. So anyway, I showed that sublimation last time or something. There's a video of it on the webpage. So Yeah, this says isochoric, they call it because it's constant volume, or it's got a fixed amount of material and volume. And then this is where you have a fixed temperature, and then you're going through the pressure volume space. So you have PV. So you can fix, you can have fixed one of these because you can have two things plotted. So you have P, T, and V. So it's going to be two things varied, the other thing held, right? So this is the isothermal plot. This is kind of complicated, and usually you only see the top part of this, right? So this thing has the entire thing in it. That's why I put it in. But basically, it also demonstrates this phase rule. So if you have a solid phase and a liquid phase and a vapor phase, right? And then you have an equilibria between a liquid and a vapor. It's at a constant temperature, right? So that the tie lines across this would be constant pressure, two phases present, right? So if you have two phases present, and you have one component, and then so 1 + 2 is 3, and you have two phases. You have 1 degree of freedom, meaning that would be along the line. So you have like a line. If you find a point where you have like liquid, if you have liquid, solid, liquid, and vapor in equilibria, so the triple point. So you have 3 phases present, and then you have one component plus 2 gives 3. So basically you have 0 degrees of freedom. That's a point. So F is 0, that's a point. That's a triple point where you have liquid, vapor, and solid all kind of coexisting together. You change the amount. So if you change the volume, you change the amount of the material in it. Like if you're within this, if you come up to this density, so you put so much material in and it's a fixed volume, so you get a specific volume that's here. And then if you, let's see, or if you fix a pressure and you change the amount of material in it, it's going to move along this line, left and right, and that would give you more. If it goes to the left, you're going to get more liquid. If it goes to the right, you're going to get more volume, more vapor, right? But the thing is at the same pressure all through that. Anyway, so this is the isothermal phase diagram. I guess you should be able to kind of sketch this out. Like in the old days when we did a oral qualifier, they'd say like draw the isothermal phase diagram. I'm not sure what use it is, but basically, so there's like a question would be like draw the isochoric phase diagram for water or something. You'd have to kind of draw this picture. And then I'm not sure, anyway, to me, it doesn't matter that much if you can do that or not, but basically you should be familiar with these kind of plots, I guess. Maybe thing is like no one ever really works in this space exactly unless you're in that space and you know this really well. So offhand is not necessarily, you could redraw that. Let's see. So, all right, yeah, it's a good place to quit here. So yeah, so I'll go through a little bit more of this next time, and I'll go through the homework paper, which is kind of a somewhat complicated one. Like you have to do a Legendre transform in it, so with a magnetic field thing. So I'll start here because it says the magnetic field component, and I'll go through that next time. Yeah. So any questions or anything on this? All right. So anyway, so yeah, so it's the homework's posted if you want to glance at it. So, that works.